studied for a long time in the literature. And so yeah, so somehow sure polynomials end up connecting to a work of several different mathematicians who I named in my abstract. So I'll describe the. So as I said, sure polynomials connect to three different areas. I arrived at this connection through one of them. So let me start and present it in the journey in the order through which I arrived at. Yeah. So nowadays I primarily study positivity, matrix positivity, and the notion of positivity in more broadly is one that has been studied in several different settings and analysis, especially, and some of the prominent flavors that I, let's say, have been looking at are as follows. The first one, the main one for this talk, is that of positivity of matrices. So for this talk, all matrices are real and symmetric, and a matrix is positive semi-definite. Basically just means that, the quadratic form that it gives you is positive semi-definite, meaning U transpose AU is non-negative for all input vectors U. Then there are positive definite sequences or doublet matrices. These are coming from sort of measures on the circle and analysis. Hilbert space functions, positive definite functions on metric spaces and topological groups, which is of course famously Bochner and Way and other people. Yeah. And one question that has been studied for quite a long time to understand the operations that preserve positivity. So as I said, I will prominently focus on just the matrix part of it. So let me set some notation. 1 second. Okay, so yeah, so given an integer n, domain I, let Pn of I, the n cross n positive semi-definite matrices, I will just call them positive, whose entries are in I. So probably when you hear Nikhil talk, he will talk about matrices whose spectrum has certain properties or whose eigenvalues lie somewhere. I care about the entries. Well, I do care about the eigenvalues in that they must be non-negative. But as far as my the operations go, I care about the entries. So once you have a function with a matrix with entries in I and a function whose domain is I can act by the function on the matrix entry by entry. And a question that that drives some of my research is, for which functions is it true that if you start with a matrix that's positive, then you end up with a matrix that's positive? And so it's not hard to come up with some examples. So the function fx equals x clearly works, or fx equals 5x works because you just rescale the matrix. But so does fx equals 1, because because the matrix of all ones is a positive semi-definite matrix. So in fact, if you look at it in this kind of a definition, if I have f of a satisfying this property and g of a satisfying this property, then you clearly know that 2 times f of will also satisfy the same property. That if f of a is positive semi-definite, then twice f of a as well. Or similarly, the f of a plus g of a also is positive semi-definite if both of them are. And so that already tells you some relations among the class of functions that preserve positivity. They're closed under taking positive multiples, sums, basically positive linear combinations. And similarly, the class of matrices of such matrices is closed under taking pointwise limits or entry-wise limits. So the class of functions is closed under taking pointwise limits. An interesting extra property was actually more than 100 years back. So this question has been studied for quite a long time now. And that property is that this class of functions which preserves positivity is closed under taking products as well, because of this thing called the Schur product theorem, which says if you have 2 matrices A and B satisfying this condition, then usual A product B times B need not even be symmetric. Okay? But A Schur product B, which is the entry-wise product, in this easy way to multiply matrices, satisfies the same property. It is also positive semi-definite. Okay, so this was proved by Schur, as I said, more than 100 years back. And as a result, the class of functions preserving positivity is also closed under taking products. So because x lies in the class of functions, so x, x squared, x cubed, and so on, all of them lie in the class of functions. And as I said, you can then take linear combinations, pointwise limits, and this was again noted almost 100 years back by Polya and Zigo in their famous book on problems and analysis. And they said that, well, just as a direct consequence of basic properties and the sure product theorem, if you take any power series with non-negative coefficients, then it preserves positivity for matrices of all sizes when applied entry-wise. So not to the spectrum, but to the entries. And they asked the question, is there anything else? Are there any other functions? And this took quite a long time to answer, but eventually the answer turns out to be no. If f is a positive semi-definite matrix, so if f is, any continuous function, f is a function, And then Schoenberg, who was a student of Schur, proved about 17 years later that for all matrices of all sizes, if the function preserves positivity, it must be exactly of the Polya and Szego form. There are no other functions that work. So this is a very nice, happy ending to the story, if you will. This continuity was removed later on. So Rudin proved. So first of all, there is a result that works on -1, 1 closed, where f need not be continuous. That has been solved. And with the same kind of assertions, except there is two more functions than the monomials, which you must include. Those are the limit. And Rudin, but then Rudin gave a variant where he looked at open -1, 1. And in that setting, Rudin showed in 1959, so 17 more years later, that so first of all, 2 implies 1 is from 1925. If f is of this power series form, then it preserves positivity. What Rudin showed is you don't need to preserve positivity on all matrices of all sizes to get to the power series description. It's enough to preserve it on Toeplitz matrices of all sizes. So Toeplitz means that all the diagonal entries are the same, all the super diagonal entries are the same, all the sub-diagonals are the same, and so on. Okay, and you don't even need all of them. You just need the ones with very low rank of less equals 3 in arbitrary size dimension n. And if you preserve positivity on all Toeplitz matrices like that, then again you get to the same description. F must be a power series. And for this, I need open interval because the closed interval doesn't quite work. So, and then very recently, then we were able to extend this prove the exact same variant. So Toeplitz matrices essentially arise from positive or non-negative measures on the circle, and you take the Fourier still just coefficients of those. Instead, if you take measures on the real line, then one can use some kind of maybe harmonic analysis than Fourier analysis to prove the same exact statement, which is if you take all Hankel matrices of rank less equals 3 again, and you preserve positivity on those matrices, then again, you must be a power series with all non-negative coefficients. So this is these are both sort of strengthenings of Schoenberg's theorem, except I remove the endpoints. And then I don't need continuity, I don't need all sizes, and I can even impose some additional structure on these matrices. So this was the kind of thing we were looking at for the last few years, matrices and preserving positivity. Let me just, before I bring in Schur polynomials and how they came into the picture in positivity preservers, let me quickly tell you why what Schoenberg was doing, because this in itself is a beautiful chapter of mathematics. I don't have time to cover it. It itself can be a 1-hour talk easily, but let me at least give you the first striking result. How did matrix positivity show up? Okay. So this showed up from the idea of distance geometry and positive definite functions. So positive definite functions are really functions that you apply entry-wise to distance matrices coming from metric spaces. So this entry-wise action comes really from there. But anyway, let me go even earlier and come to Schoenberg's story. How did his 1942 paper show up? So in the late 1900s, Frechet, Birkhoff, Hausdorff, and others were working on metric spaces, formalizing the notion, and then studying basic properties. Of course, now it shows up everywhere in mathematical sciences. And here is a sample result. So Frechet showed that if X is a metric space of size n+1, then it isometrically embeds into Rn. And then now, since then, one has improved. Witzenhausen helped improve this to Rn-1 for, I think, n bigger equals 2 or 1 or something like that. But anyway, so Frechet showed that every finite space embeds into the sup norm metric. And then, of course, in the early 1900s, it was natural to ask which metric spaces embed into Euclidean space, into the real world, if you will. So there were some characterizations provided in the 1930s by Frechet and Menger and so on. And then Schoenberg recast one of these results using matrix positivity. And so this is not 1942, but this is his first paper along these lines, first result maybe. And he said that, so here is his result. Fix a finite metric space of size n plus 1. Then that embeds isometrically into a Euclidean space, an L2 metric. But and he also tells us what is the smallest size to which it embeds. Okay, of course, once it embeds in one space, it can embed in everything bigger. But what is the smallest size? So, well, it embeds into the smallest size if and only if this particular matrix. So remember that a metric space, the entire information is encoded by its distance matrix, Bxi, xj. So I take that matrix, former, that should be an n plus 1 cross n plus 1 matrix. I form the related n cross n matrix in this way. And that has to be positive semi-definite. Only then X can isometrically embed. So suddenly it connects Euclidean embeddings to positive semi-definiteness. And the smallest dimension is the rank. So that's how Schoenberg connected these two seemingly different areas. And this matrix A is called the modified Cayley-Menger matrix. So it goes back to work of Menger, but also to Cayley, maybe 100 years before that. So yeah, it's a beautiful area of mathematics, and it's really, Schoenberg provided another beautiful connection to matrix positivity. Okay, but so Schoenberg was interested, and Rudin and others, in functions preserving positivity in all sizes. And eventually from 1935 to 1942, he studied positive definite functions in his paper in Duke. At the same time, Bochner and, at the turn of the decade, in fact, Bochner and I think Rykov and Way and other people had worked out Bochner's theorem over locally compact abelian groups and so on. Schoenberg studied it over metric spaces using a different notion of positive definite functions than the one over groups. And that is what led him to infinite dimensional spheres of Euclidean type and to entry-wise preservers in all dimensions. Okay, but so since Schoenberg and Rudin, several other people have studied the problem of entry-wise preservers in this setting and related settings. And one can, of course, the natural thing to ask after Schoenberg's theorem in 1942 or Rudin and so on is, what about I do the next refinement, which is I fix the dimension of my matrices and then understand preservers. Okay? So this is mathematically a natural refinement, but also it comes up in high dimensional covariance estimation, where one knows the dimension of the problem, one knows the number of random variables, so I don't need to only use power series with positive coefficients. I can try to understand, and there are many other functions that work in a fixed dimension, like powers which are not integer powers. What is known about this problem? So it's natural to understand all the functions that preserve positivity in a fixed dimension. For 2 by 2, this was already done by Vasudeva, almost 45 years back or something. And this is the condition. It's not very difficult to understand. For 3 by 3 matrices, the problem is still open. So we still don't know a complete solution to which functions, when applied entry-wise, preserve positivity. And essentially, what is known for a general function is a necessary condition by Charles Loevner, which eventually appeared in the PhD thesis of his student Roger Horn, who is the author of Horn and Johnson Matrix Analysis, one of the classic books in the area. Of course, Horn did his PhD more than 50 years back from Stanford, and so Loevner. Loevner, of course, passed away, I think, in 1968. So Horn's thesis, this paper, was published later, but he had originally summarized his calculations in a letter in 1967, and I actually have so the point was, I used to work at Stanford before my present job at ISC, and Loebner was a faculty at Stanford. So when he died, all his boxes of mathematics and unfinished calculations and papers were given to the library. So I went one day to the library and I was browsing through his folders, and I found the letter that I mentioned here to Josephine Mitchell in 1967. And here is the copy of that letter. So Loebner said that he got interested in the following question: let f of t be a function with no restrictions, let's say, for now, defined in some interval AB in the positive side, and consider all real symmetric matrices, so positive semi-definite matrices, of order n with elements in that set. Bigger than 0 means positive semi-definite. The eigenvalues are non-negative, and the entries are in that AB. Which properties must F have in order that the matrices F of Aij entry-wise are So he was interested in this for the reasons of sort of Schlicht functions and or univariant functions and Beaver-Buck's conjecture. He believed it would help him make some progress, and he did have some results along those lines before, of course, Debran just proved it. But anyway, he was interested in this function and this question, and specifically in the case of power functions, it seems. But he asked the general question, and he found that as long as f is n-1 times differentiable, the following conditions must be satisfied. Okay. The function, its derivative, and so on. The first n derivatives from order 0 to order n-1 must be non-negative. Okay. And as I said, he was interested in power functions, and he checked that the power functions don't satisfy this property for, this condition. The number of derivatives here is sharp because of power functions not satisfying the higher order derivative condition. And the proof, he said, was using some things that I will come to later in this talk, in the last part of this talk. But okay, so there was this negative, so there was this essentially the only known condition. And now, so let us apply it then to a special case, which is polynomials. So sort of Schoenberg and Rudin said that if I have a power series or a polynomial with all positive coefficients, then it will work to entry-wise preserve positivity in all matrices and all sizes. Right? So if I want to only preserve positivity in a fixed number of fixed size matrices, that's a much smaller set of matrices. So I should expect a much larger class of functions to work. So for in particular for polynomials, I would like to, of course, understand if anything more than the ones that Schoenberg and Rudin found from this, or actually Polya and Zigo found in 1925, does anything more than those 1925 class of polynomials preserve positivity in a fixed dimension? Meaning, is there at least one polynomial with one negative coefficient that works? Now, first of all, what Loebner's theorem said is that if you have these coefficients, then the constant term, which I called C1, change of index, C2, Cn-1. So all those C1, C2, Cn must be non-negative. So that's what Loebner says. So that much is guaranteed, that is necessary. Can the next higher, so let's take a polynomial with n plus 1 monomials. I can take the last monomial to have degree n or anything higher. And now I can ask, can that leading term be negative? So, and remarkably, as I said, so if the leading term is non-negative, then by the sure product theorem, this works for everything. That was known from 1925. But until 2016, which is almost 100 years later, not a single example was known for n bigger equals 3. For 2 by 2, Vasudeva's result gives us the answer. 3 by 3, even this was not. So it was very little was known. People had been working in fixed dimension with other refinements like power functions and so on, or in all sizes with other refinements like Toeplitz matrices. And there are other variants that I can tell you about. But for instance, for polynomials, this was not very well understood. More generally, I don't need to take consecutive monomials here. I took degree 0, degree 1. I don't need to take that. I can take non-consecutive monomials. And then again, one can argue by some similar argument of like Loebner, or even simpler, that the first n non-zero coefficients must be positive. Can the next one be negative? So this is sort of the more general question. That's the toy case. This finally did turn out to be true. It can be negative. And so this is the result that we proved last sort of in December. So barely 4 months ago, it appeared. So, and the result says the following: take any polynomial with real coefficients and fix a dimension n and let the polynomial have n plus 1 monomials. Nothing more. You can tackle the case of more monomials using this case. So this is really the case that underlies all of the remaining ones. Okay. As we said, these first and lowest degree coefficients, these are the degrees, have to be strictly positive. And so here is the result. So first, the following are equivalent. The function preserves positivity on n cross n matrices of all sizes. Of a fixed size for fixed n. If and only if either all of these coefficients are non-negative, that is the 1925 result of Polya and Zigo. Or the first n are strictly positive, that's like the 1969 result of Loebner. And this leading term is allowed to be negative. It is at least it is some negative number onwards, something bigger than that. This threshold is given by this explicit formula. There's an explicit formula in terms of these coefficients and the powers, and that's all. And the size basically. I am only allowing matrices to be like correlation matrices or matrices with sizes between 0 and 1 and so on. Then there are variants for -1 to 1, complex entries and other kinds of things. But for this talk, I will work only with matrices with positive entries. And this term in red, this product in red is highlighted because it is going to tell us about, it's connected to Schur polynomials. So every time you see something in red, think in your mind of Schur polynomials. I've tried to make these connections. So in fact, it's going to turn out to be an unknown connection to Schur polynomials. Let me put it that way. Okay, so yeah, so this doesn't quite look like a Schur polynomial, which I will define very soon. Anyway, the other surprising thing for us was that this sharp constant is attained on the boundary of this sort of set. If we care about the rank 1 Hankel matrices, and the rank 1 again structured but also low rank. So really the things that occur on the boundary of this test set are enough to understand the functions, that the polynomials of this kind that reserve positivity on all matrices. 2 comments. This holds even if these, as I said, these degrees were integers, they need not be integers. Even then, this explicit formula for the threshold holds. The same result is true. And the second case is, yes, this is of course in 2021, but we knew the simpler setting, this setting where the degrees were initial and consecutive, that was known for, as I said, since 2016. That was the toy case, but there are subtleties in this more general setting that did not appear there. We had to, for example, the key subtlety was we had to maximize a ratio of 2 Schur polynomials. And over here in this thing, the denominator in that ratio was 1. So we had to maximize a polynomial. And that was that was trivial because of the polynomial having positive coefficients. In this case, that is not the case. And so I'll show you that polynomial in a couple of slides. So to lead to the key player in all of this, Schur polynomials, let me tell you how this number, this red quantity occurs. So it's the square of some quantity, and that quantity turns out to be arising from a Schur polynomial. And it arises in sort of the sense of representation theory. So Schur polynomials actually turn out to be characters, formal characters of polynomial representations of the general linear group or finite dimensional irreducible representations of the special linear Lie algebra over complex numbers. So because they are characters of some representations, when you specialize the character to sort of the identity element in the torus, 1, 1, 1, 1, 1, they give you the dimension of that representation. And that's called the Weil dimension formula. And the dimension of some representation is exactly something like this. Remarkably, this number is always an integer. It's some fraction of numbers. It turns out to be an integer. Actually, no. Sorry, not this number. A closely related variant is an integer. Sorry, this is a ratio of 2 integers, which I will show. Okay. But the key point for the result on the previous slide is that we look at these very algebraic objects. These are the characters of representations of some reductively group. We are looking at them as functions of scalars, of numbers, n1, n2, nk. So we're looking at these numbers. So, and that's the key to solving that problem in analysis. So, and sort of, we were lucky that, in some sense, algebraists did not know of the problem, analysts did not work with Schur polynomials. So luckily we were at the right place at the right time, and so that led to this solution. So let me now define for you what is a Schur polynomial. It's very, very simple, and I will give you two examples on the next slide. And you can even compute Schur polynomials using pictures rather than some determinants. But here is one definition. This is due to Cauchy, maybe almost 200 years ago. Take the generalized van der Waals determinant. So take some variables, u1, u2, un, take integer powers, n1, n2, nn, if you will, and look at the generalized van der Waals matrix. Now you see that if I switch the role of ui and uj, or u1 and u2, then the determinant becomes negative because the rows are exactly flipping. Right? The moment you have a polynomial, so, and also this, of course, the numerator is a polynomial. So if I have any determinantal polynomial like this and I invert two variables, I get negative sign, that must be divisible by u1 minus u2. Okay? That's well known. And so in particular in the UFD, this numerator is divisible by product of ui minus uj, or ui minus uk, which I don't want to use j. But that product is precisely the van der Waals polynomial, the van der Waals determinant, right? The usual van der Waals. So I can divide the generalized van der Waals by the usual van der Waals, and I will get a homogeneous symmetric polynomial in these n variables. And that is called the Schur polynomial. And I'm just writing V of U to be the Vandermonde of U1, U2, UN. Okay. Great. So these Schur polynomials, as I said, are characters of irreducible polynomial representations. But they also, they're very well studied since Cauchy defined them, let's say, 200 years back. But then they appeared in Schur's thesis, and that's how they got their name. They form a basis of homogeneous symmetric polynomials in these many variables, and in fact also in infinitely many variables. Symmetric function theory is this whole branch of mathematics they have spawned, and in the context of symmetric function theory, they are usually defined in terms of semi-standard Young tableau, because then you can define them for infinitely many variables. But here are and anyway, I'll give you two examples, as I said, on the next slide. But here is one more property they satisfy. Because these are polynomials, I can specialize to 1, 1, 1, 1, 1, which I cannot do in this definition, right? The UIs cannot be equal because I'm dividing by their Vandermonde term. But nevertheless, 1, 1, 1, 1, 1, yeah. And so when I specialize them to 1, 1, 1, 1, 1, I get exactly the product that I told you about on a couple of slides before. And that is the ratio of these two Vandermonde terms. Okay. So, by the way, of course, feel free to ask me questions and interrupt if you have questions. I should have said that at the beginning, sorry. So this is the definition. This is one definition of the Schur polynomial, which is very simple. And this turns out to give this formula upon some specialization. So, okay, now this is the other. So now here is the pictorial definition, if I will. Yeah. Schur polynomials are also defined using these semi-standard shapes called Young tableau. Let me give you two examples. Let M, so they are defined using a tuple of variables and a tuple of powers, integer powers, which are here. So let me take M to be 0, 2, and 4. So I have 3 powers and 3 variables. And the idea is, because I'm dividing this. So what is a typical monomial here, right? It would be U1 to the 0, U2 to the 2, U3 to the 4. I would be dividing this determinant by the Vandermonde determinant, which has U1 to the 0, U2 to the 1, U3 to the 2. So when I divide by 0, 1, 2, what do I get? I get 0, 1, 2. So I create these diagrams where there are 0 cells in the bottom row, 1 cell in the next row, and 2 cells in the top row. 0, 1, 2, which is this minus 0, 1, 2. That's what these number of cells in the row are. Right? And for each such diagram, now I have these diagrams, empty boxes. I fill it up with my alphabet, which is 1, 2, and 3, because n equals 3, with the following rules. Entries along a given row must be weakly decreasing from left to right. So they are 3 and 3, or 3 and 2, or 3 and 1. Entries along a given column must strictly decrease. Okay. That's called, so these are called semi-standard Young tableau with this alphabet 1, 2, 3, and this shape 0, 2, 4 minus 0, 1, 2. Okay, and then it's very simple. My Schur polynomial for this setting is literally U3 square U2 plus U3 square U1 plus U3 U2 square, and so on. It's literally just the sum of these monomials. These two monomials in the middle give me U1, U2, U3. So I have a coefficient of 2 in front of that. Great. And you can check that this polynomial exactly factorizes in this form. And that is not hard to check from the Cauchy definition as well. That's why I chose this particular tuple of powers. What is this? This is literally the determinant of U1. So U1, U2, U3 raised to 0, 2, and 4. But that's the same as U1 square, U2 square, and U3 square raised to 0, 1, and 2. It's the usual Vandermonde determinant for the squares of the variables. That's the numerator. The denominator is the usual Vandermonde determinant for the variables. So the ratio, therefore, would be the product of uj square minus ui square divided by the product uj minus ui. And we know that a square minus b square over a minus b is a plus b. Hence, this factorization here. It's literally the product of uj plus ui. So that's why you see that this polynomial equals this rule. So I told you why this definition due to Littlewood equals the other definition due to Cauchy in this special case. Right? And actually, if you have seen some representation theory, for example, for SL3, if you have seen the adjoint representation, SL3 itself, then you would have seen this nice picture of a hexagon. It's an 8-dimensional representation. The space of SL3, the traceless the trace 0 3 by 3 matrices has dimension 8, right? And the 0 dimension, there's a weight, there's a ring around the point 0 because that 0 weight space eigenspace is dimension 2. Those are the two diagonal matrices, the two-dimensional diagonal matrices with trace equal to 0. So that's exactly the point here. This is the character of that representation, and the 2 here exactly corresponds to the weight 0 weight space. Anyway, but we won't look at the representation theory side in today's talk. We will look at the analysis side, where we look at these polynomials genuinely as polynomial functions with all the u1, u2, u3 being strictly positive. Right? Because as I said, in my matrix calculations in this paper with tau, we wanted to look at polynomials preserving entry-wise positivity of matrices with positive entry. So the u1, u2, u3 have positive entries. And it is u times u transpose, that's the rank 1 matrix on which they act by the function. Okay, so here is another matrix. Here is another Schur polynomial. The entries are 0, 2, and 3. I will denote that tuple by n. So again, I must look at the shape being this minus 0, 1, and 2. That's 0, 1, and 1. So here, like this. Now, entries strictly decrease, so there are far fewer possibilities. In fact, only 3 of them. And the Schur polynomial for this is exactly u1, u2 plus u2, u3 plus u1, u3. I wrote them in some cyclic order. Now, notice one thing about these Schur polynomials, right? So, from the previous definition, from here, I know that the Schur polynomials are homogeneous and symmetric. Just algebraic division of some alternating polynomial by the band. I don't know anything about the coefficients. The coefficients are rational numbers. They don't need to be integers. And the coefficients are rational numbers. They don't need to be non-negative either. From this definition, that you take this young tableau of some shape and fill them with letters, I immediately see that the coefficients of my Schur polynomial have to be integers and have to be non-negative integers. But I don't see that the Schur polynomial is homogeneous or symmetric. There is no reason why, from this definition, u1, u3 square and u2, u3 square have the same property, or u1, u3 square and u3, u1 square have the same coefficient. So it's really both of these definitions together that give you all these rich properties of Schur polynomials. But anyway, the point is, so Schur polynomials are this beautiful class of symmetric functions, which are also monomial positive. All they are sums of monomials. There are no negative terms, and the coefficients are all integers. Okay. Okay, so they're monomial positive, and they are symmetric and homogeneous. And so in particular, as I said, I want to look at them as functions on the orthant. So when I look at them as functions, because they are sums of monomials, they will always be coordinate-wise increasing or non-decreasing at least. So, yeah. So now let me look at, so the key interesting thing that was the key behind this main result of positivity preservers, why it was not known since Schur's time, was because of this result that we need. We need to look at ratios of Schur polynomials. So that's why I defined 2 of them on this slide. I want to look at the ratio. And the key point is that the term by term, 0 dominates 0 in the powers, 2 dominates 2, and 4 dominates 3. Okay, so I want to look at m and n, where the entries of m coordinate-wise dominate the entries of n. Okay. So, yeah, so both the numerator and denominator are monomial positive. And in fact, they are Schur positive. Schur positive means they are sums of Schur polynomials because they are exactly one Schur polynomial each. Okay. And now, therefore, they're of course non-decreasing in each coordinate. The remarkable fact was that the ratio has the same property when you look at it as a function on the positive orthant, as I want to do in this term. And this is sort of the main technical underpinning of our results. Take any number of course, integer powers, so long as nk is less equals mk, this function is non-decreasing in each coordinate. And in fact, a stronger Schur positivity phenomenon holds, which I want to tell you about. So really, this talk is about Schur polynomials. Let me tell you how they show up, not just in this numerator and denominator, but in the proof. Okay, so, and the reason why it happens, let's just do it in a special case, is how do you prove that something is coordinate-wise non-decreasing? Well, first of all, this is a symmetric function of 3 variables. So it's enough to show that it is non-decreasing in U3. How do you show it's non-decreasing in U3 or in X, Y, and Z? It's non-decreasing in Z. Well, you do, first-year calculus, right? You just apply the quotient rule of differentiation. So you do low D high minus high D low, and you check that it is equal to some expression like this. This clearly is a sum of monomials, and therefore it is numerically positive. It's non-negative. When you evaluate the monomials on the positive orthant, Of course, you get positive real numbers, and so you get what you want, right? But it's actually stronger than that. So the first thing is because you differentiate with U3, you don't expect low D high minus high D low to be monomial, to be symmetric in U3 as well. But certainly it's symmetric in U1 and U2. So let me write it as a polynomial in U3, whose coefficients are symmetric polynomials in U1 and U2. When you write this down, what you see is that because there's a U3, the constant term in U3 is 0. The linear term is the one where they have 2u1, u2 times this. So it is 2u1, u2 square plus u1 square u2. That is twice this plus this. And guess what? This is a Schur polynomial in u1 and u2 in one less number of variables. It's exactly a Schur polynomial. Similarly, if I look at the quadratic term, I get u1 plus u2 square, and that is u2 square plus u1 u2 plus u1 square plus u1 u2. And the cross term, this cross term is a Schur polynomial. These three terms make up a Schur polynomial. So again, it's a sum of two Schur polynomials in a fewer number of variables. And this is what happens. The coefficient of every monomial in U3 is Schur positive in fewer number of variables. And that's the same thing that happens in general. Right? So by symmetry and the quotient rule, it suffices to show this for a general capital N number of variables. And that turns out to be, these coefficients turn out to be skew Schur polynomials inside the Schur polynomial, but they also turn out to be the same thing inside this expression. And it would follow if this expression was monomial positive, but in fact it's Schur positive as well. And the key behind that is some result of Lamb, Postnikov, and Pilyavsky in 2007. So that's some result that shows up from the results on Marx, Kandera, and others. This result itself was a refinement of results on Marx, Kandera, and others. Okay, so that was sort of I think that was the end of the first part of the talk, where I told you how we worked on this old program of Schur and Polya and Zigo and Loebner, several Rudin, Schoenberg, several others, and came to this question in a fixed dimension: which polynomials, can there exist polynomials with negative coefficients which preserve positivity on 3×3 matrices? And even that was not known, and now the answer is known because of Schur polynomials. The key to answering that question. But Schur polynomials then turn out to play a crucial role, starting from this very monotonicity lemma that I told you, going into two different other directions. So the first one is in terms of weak majorization and majorization. So this is something that you can define for tuples of real numbers. These are just fundamental inequalities that show up all over the place in theory and applications. But so here is so what we showed was that this ratio of two Schur polynomials is coordinate wise increasing, right? So whenever u has all coordinates 1 or above, the value at u beats the value at 1, 1, 1, 1, 1. And as I told you, the while dimension formula says that the value at 1, 1, 1, 1, 1 is exactly this divided by the van der Waals. So the two van der Waals divisions cancel, and what you get is this ratio. So the value at 1, 1, 1, 1, 1 of this ratio is the ratio of the van der Waals. And if m dominates n coordinate wise, then the Schur polynomial here beats the Schur polynomial at u. Okay. It was natural to ask, okay, for which other tuples does this inequality hold? Yeah. Is it only when m dominates n coordinate wise? The answer turns out to be no. So, and this answer turns out to be no, one can even extend it for real sets of powers. So what is a Schur polynomial for a real tuple of powers? Well, remember that the Schur polynomial was the ratio of a van der Waals determinant, generalized van der Waals, by the usual van der Waals. So if I put in that in both numerator and denominator, the usual van der Waals cancel, and I get this ratio of generalized van der Waals. And that is the theorem that we proved. So this is a second offshoot of that Schur monotonicity lemma. It was useful for positivity preservers. It's also useful for weak majorization. So given two real tuples, and I don't need negative, non-negative, or whatever, I don't need integer powers, this ratio beats the ratio of the van der Waals. The only thing I need to restrict to is these u's cannot have the same argument, because I need to divide by generalized van der Waals matrices. So let me take distinct tuples, meaning tuples in 1, infinity to the n, but pairwise distinct components. Right? This happens if and only if m weakly majorizes n. So what does weak majorization mean? It means that the highest entry of the tuple m is bigger than the highest entry of the tuple n, the sum of the top two beats the sum of the top two, and so on and so forth. Some of the ingredients of the proof are inherently algebraic. But there's also some analysis. There's a first order approximation, or the leading term to compute of sure polynomials or of the generalized van der Waals determinants. And there's the Harish-Chandra-Isaacson-Zuber integral. There are some sure complexity results. And together these the proof is fairly technical, but the result is very clean. That you take the ratio of two sure polynomials or just of two matrix van der Waals determinants, and that beats the value of the ratio of the two into the power van der Waals determinants for all distinct tuples if and only if M weakly majorizes N. So it's a symmetric function. This is sort of a symmetric function identity. Whether, of course, there's functions on the orthogon. And this remarkably turns out to be connected to weak majorization, which is the inequality identity, sort of two seemingly distinct areas. What I want to tell you now is this is not quite seemingly new. This has been studied from about 200 years back, or maybe 300 years back. And that's the focus of the next few slides. So even in this setting of majorization for sure polynomials, this was studied about 10 years ago. But they didn't, so by Cutler, Green, and Marx-Kandera again, whose results underlay the Lamb-Postnikov-Belyavsky theorem I mentioned, they studied what happens not only when the values are bigger than 1, but when the values are bigger than 0 on the entire positive orthant once again, like we were doing in our monotonicity lemma. And here is their theorem. So what they said was so they studied it for integers, fixed sure polynomials again. When is the ratio of two sure polynomials on the positive orthant, but now on the entire orthant, bigger equals the value at 1, 1, 1, 1, 1. Yeah. So clearly, okay, when is it bigger than 1, 1, 1? This cannot happen when M coordinate-wise dominates N unless M is equal to N. Okay, this is one result. But what happens is this happens if and only if M majorizes N. So these three authors proved they proved that if this happens, then M majorizes N. And they conjectured that the converse holds, and Suvrit at MIT proved the converse about 5 years later, again using the Harish-Chandra-Isaacson-Zuber integral that I mentioned. I should point out majorization is exactly the same as weak majorization, plus the fact that the total content, the number of boxes in the Young tableau equals the number of boxes in the Young tableau. So when M strictly dominates N, it means that those Young tableau contain the Young tableau for N, the shape. So how can a number of boxes be the same unless the shapes are exactly the same? M equals N. So that's why I said this can never happen unless, for coordinate-wise domination, unless N equals N. But it can happen in other cases. And so first of all, it's natural to ask the same question that we solved above. We have a characterization of weak majorization for real tuples. This is a characterization of majorization for integer tuples. So can it be extended to real tuples? Secondly, do we need the entire orthant? So, or in the fashion of this thing, can we work with some smaller part of the orthant? Here for weak majorization, we only needed the log positive orthant, the entries bigger than 1. So can we do something like that in the case of majorization? The answer turns out to be yes and yes. And so here is the next result. The following happens for real numbers, for real tuples of powers. First of all, again, I can replace the ratio of the sure by the ratio of the generalized van der Waals. This beats Vm over Vn for all distinct tuples in the full orthant with unequal coordinates. That was the extension of Cutler, Green's, Kandera, and Stra. If and only if here's a smaller tuple, right? So I take the same entries with coordinates with all entries bigger than 1, and I take coordinates with all entries less than 1, but only those two, the log positive orthant and the log negative orthant, rather than all log orthants. That's enough to prove the same thing here, and that's enough to play if and only if M majorizes M. So clearly, I want to give you a sketch of the proof. Maybe I should skip the proof here because I think I may be running short of time. But yes, basically what happens is if this clearly implies this, and if 2 holds for the entries bigger than 1, then M weakly majorizes N. And then for the entries less than 1, I take 1 over the coordinates UK, and that will help you see by minus M weakly majorizes minus N. So if you know that this holds on both the log positive and log negative orthants, then I get M majorizes N weakly and minus M weakly majorizes minus N. And those two conditions in blue together are if and only if M majorizes N. That's the end of the proof. So that's how you get 2 implies 3. And 3 implies 1 is like Harishchandra writes, it's in Zuber integrals and so on. So yeah, so that's why, first of all, one can use weak majorization to prove the majorization and for real tuples as well. Okay. So now, as I told you, some of these inequalities are examples of majorization inequalities, and they have been around for hundreds of years, apparently. So Cutler, Bean, and Scandera themselves very helpfully provide references to these old results in their paper. So what if one uses other symmetric functions than Schur polynomials? Right? So Cutler, Bean, Scandera said, now you see here, I'm switching, I'm sort of cross multiplying the terms. So earlier I have said that Sm over Sn bigger than Sm1111 over Sn11. Those are van der Waals. Now I'm saying, let's look at the normalized Schur polynomial for the tuple of powers m beats the normalized Schur polynomial for the tuple n on the entire positive orthant if and only if n majorizes m. Instead, one can use other symmetric functions. There are many of them. One is called the monomial symmetric polynomial. And there I would just look at, if I have m lambda, lambda is a tuple of powers, then I would look at u to the, so u1 to the lambda of 1, u2 to the lambda of 2, so on, plus u1 to the lambda of 2, u2 to the lambda of 3, and so on. And I sum it up over, I average it over all permutations. So uk to the lambda of sigma of k. Right? So that's the kind of permuted powers of monomials, and then I average them out. Okay. And I'm not taking -1 raised to any sign of permutations here. So I'm not doing a determinant. This is more like a permanent kind of thing. Yeah. And these are called the monomial symmetric polynomials. And for those, one has exactly the same kind of inequality. The normalized monomial symmetric for m tuple beats the normalized monomial symmetric for n for on the entire positive orthant again, exactly in this form, if and only if exactly this result. M majorizes. This is an inequality more than 100 years old, older than the Schur product theorem by Muirhead in 1903. Yeah. And in fact, this is preceded by other things as well. So Maclaurin, Newton in the 1700s, and then Schlomil Schur himself, and various other people. These are all examples of majorization inequalities. And there was recently a vast generalization by Colin McSwiggan and Jonathan Novak from this kind of majorization, the usual majorization, to all while groups. And so I want to spend a couple of slides. These are technical, and this paper appeared literally this year, maybe last, or maybe it is yet to appear this year, something like that. It is, yeah, IMRN 2022. Right? And so I'm now going from 1700s all the way till like last month or something. Yeah. So these two slides are sort of technical, and I apologize for that, but I'll get to the third and final theme of the talk after these two slides. And I should point out again that I'm not an expert on W majorization myself. Yeah. So, but anyway, let V be a Euclidean space containing a crystallographic root system with this while group. Yeah. So what does that mean? So that means that you have this root system is a finite set of vectors satisfying certain axioms, and to each such vector, of course, in a Euclidean space, you have the inner products, you have the orthogonal hyperplane. And you look at the reflections in those hyperplanes, this while group is simply the finite subgroup of orthogonal group generated by those orthogonal reflections. It turns out to be finite because these reflections end up permuting this finite set. And so the W is a subgroup of the symmetric group on that set, if nothing else. Okay, so McSwiggan and Novak define W majorization in this general setting. Right? The point is, there is a different characterization of usual majorization. Lambda majorizes mu if and only if mu, the tuple vector mu, lies in the convex hull of the elements of lambda permuted. So lambda and then so sigma of lambda over all sigma in the permutation group, they form a set of size n factorial or less equals n factorial. Take the convex hull of that. That's called a convex polytope. And lambda is set to majorize mu if and only if mu lies in that convex polytope. That is either a definition or a if and only if theorem. You can prove either. Right? Okay. And so now, similarly, we say that lambda W majorizes mu if mu lies in the convex hull of the orbit W dot lambda in this more general setting. And the point is, of course, if this root system is of type A, then the permutation, the while group is precisely the permutation group. And so lambda Sn majorizes mu is the same as saying lambda majorizes mu. So this is the usual majorization. And so now, so in these two slides, I want to tell you the sort of result that they did. That G be a connected group and sigma an order 2 involute. That means it's an involution, automorphism. If the fixed point subgroup is compact, one says that G mod K is a Riemannian symmetric space. And under further decomposition assumptions, one looks at the Iwasawa decomposition of this of the group itself. In that case, the roots, the A sort of looks like the Cartan subalgebra with the root system, and the weights of this adjoint of the Lie algebra itself with respect to this A form a crystallographic root system. So one can study W majorization for exactly for weights in this. Actually, I think there's a typo. This might be A star here. There should probably be A star here. Anyway, but if there's an inner product, and so you can identify A star and A. Yeah. And then one wants to understand. So what was so? Remember, there are two sides to this majorization inequality. One side is lambda majorizes mu. The other side is that some normalized Schur polynomial or monomial symmetric function, some normalized such function beats the values of some other normalized function on some space. What are the analogs of Schur polynomials in the general setting? These are called spherical functions, and they were studied in particular by Harish Chandra in 1958, among other things, where he found an integral representation for spherical functions. So what Maxwell and Novak did in their paper this year is they extended this Cutler, Green-Skandera, and Suvritsra characterization for real powers, for integer powers, or the extension by tau and me to real powers for usual majorization to classify W majorization on A for all these W's, for all types. And they did it via inequalities of the form some spherical function for lambda dominates the spherical function for mu on this Riemannian symmetric space of non-compact type or compact type or Euclidean space. So that's how they work this out, and that these inequalities turn out to subsume lots and lots of these past inequalities I mentioned to you on the previous few slides. This is a vast generalization, and of course I will refer you to their paper for the technical details. Yeah, but so this really has found starting to get to its culmination from early work by Maclaurin and Newton from 1700s to like Schlomilch and so on, to even this past decade by Cutler, Green, Skandera. And these are for sure polynomials or spherical functions, but these are now conjectured to hold even more generally for Heckman-Ogden hypergeometric functions. And in that case, again, they have proved, Maxwell and Novak in this paper, proved the Cutler, Green, Skandera side of the implication. If some hypergeometric function for lambda beats some hypergeometric function for mu, then lambda majorizes mu. So they proved that easy half, quote unquote. The problem is there is no difficult half. The converse part is not there for Harish Chandra. There's no sort of Harish Chandra, and Zuber integral analog for the Heckman-Ogden hypergeometric functions that can be used in their manner right now. So that converse part is still a conjecture. But if it were true, it would extend these things from Schur polynomials to Jack polynomials. And it would also therefore imply Muirhead's inequality. So Muirhead doesn't quite follow from what Maxwell and Novak have done so far, but it would. And then the pipe dream, of course, is to formulate and extend from Jack to sort of this two-parameter massive generalization of Schur and Jack and others called McDonald polynomials. But that's again the whole new semester course in itself, McDonald polynomials. So let me stop with this part right now. Okay, so in the final few minutes and my final few slides, I will go back to, so I'll go to the third calculation. There's a third line of work that, again, these results extend. And actually, more precisely, Loevner's 1967 letter extends more than 50 years later. So I'll remind you what Loevner was doing was Loevner wanted to understand some entry-wise functions that entry-wise preserve positivity in a fixed dimension on matrices with positive entries. Or we can say non-negative entries, it's fine. So, and his idea was very, in its essence, the idea was to say, fix a tuple of U's with pairwise distinct positive real scalars and look at the matrix T times U transpose. These are these rank 1 matrices which Tau and I also work with, which Loevner worked with, and so on. And take the determinant of this. So if the function preserves positivity, then when you apply the function entry-wise to this matrix, it should be positive semi-definite. So its determinant should be non-negative. And then Loevner looked at the Taylor coefficients of this determinant and deduced the non-negativity of those derivatives. And so he had to calculate the first n choose 2, capital N choose 2 plus 1 derivatives in his proof. Okay. The proof was for smooth functions, in fact. The calculation was for smooth functions. So it turns out, and this is what Loebner actually showed in 1967, that the first n choose 2 derivatives are all 0. So literally, here is the question. Now forget Loebner, forget MacDonald and Maxwiggen and majorization. Just look at the following simple question. Take a smooth function, take pairwise distinct positive scalars. Look at this function of t. Delta of t is apply the function entry-wise to t times u transpose. That's a matrix, a square matrix. Take the determinant. That's a function. Compute the Taylor coefficients of this function. That's it. It's a calculus question. There's no Loebner around anymore. Just think of this question, right? But what Loebner showed, he did this, he worked out this calculus question, and he showed that the first n choose 2 derivatives are 0. Just plain 0. And the next derivative, and let me normalize it by the factorials, obviously, that is equal to the Vandermonde of u, quantity squared, times the quotients of these derivatives, right, by their normalizations. And that was it. So the point is, in his letter, he writes everything here except the 1 square in red. And the point is that 1 square is a very, very key factor lurking inside, hiding inside this calculation. And it was sort of lucky, or maybe unlucky for the field, but maybe lucky for me, that Loebner did not go one step further. What if he had? So he stopped here because he wanted to understand entry-wise functions preserving positivity. But what if you go one step further and you calculate the n choose 2 plus first derivative at 0? Then you would get the same normalization here, the same Vandermonde square here, the same kind of ratios of derivatives here, and the n minus first derivative, the last term, gets replaced by the nth derivative. But what you also get then is a different Schur polynomial, a different symmetric function squared, and that is the Schur polynomial, think pictorial, for the box with exactly one box. Then that one box can be filled by letters from 1 through n. You add them up, you get u1 plus u2 plus un. And then the square. So if Loebner had gone one step further, he would have found this symmetric function hiding inside the derivative. And that's what helps us provide, so this provides a novel bridge between analysis or smooth functions and symmetric functions. Given a smooth function here, given pairwise distinct scalars, set delta up to be this thing and calculate all derivatives. And this is now one can do this. There's a closed form expression, and one can do this actually. You don't need to have u times u transpose. You can have u times v transpose, and that doesn't matter. And you can check that what you get is this mth derivative is a sum over all partitions, all boxes with exactly m many total boxes, all shapes with m boxes. The Vandermonde of u, the Vandermonde of v, hence you got the square. The Schur polynomial of those box shape for u times the Schur polynomial for v times the ratio of the normalized, times the product of the normalized derivatives. So really, as you take m higher and higher, all the shapes will occur because every shape has some number of boxes and they all occur. So all Schur polynomials sort of are hiding inside every single smooth function. Of course, if the derivatives are 0 here, then you get 0. So you never see those boxes, but morally speaking, they are lurking inside. And the last thing to do is to tell you about this old area of mathematics, which actually now connects to this. If f is a power series, suppose I start with a power series, then of course the right-hand side here, this determinant, is also a power series, right, with some radius of convergence. What is the expansion of this power series in terms of the power series of f? This turns out to have a very long history again. And I told you that Schur polynomials were defined by Cauchy initially, the Cauchy definition. Well, with that definition, Cauchy actually answered this question, that if I start with the geometric series, 1 plus t squared, and do this calculation, then all these numbers are just ones, and what I get is just Vandermonde of u, Vandermonde of v times the summation over all m of this thing. I get exactly that expansion. And that turns out to be a special case of a calculation by Frobenius in the 1880s, also still 1800s, where he looked at a sum of two geometric series, 1 over 1 minus t, minus ct over 1 minus t. And then he got something very similar looking. So of course, it's natural to ask, can you do something more general? What about other power series? And similar questions have been followed up by many people, followed upon over the last few decades. At least there are even 2 beautiful survey articles by Christian Thaler, where he covers some of these results and others. But the answer finally is true, and it's true completely algebraically, or it's true in sort of the locally in some radius of convergence. The answer looks the same way. Take any unital ring R, take any indeterminate T, and take any formal power series f of t. Given any 2 vectors in R to the n, we have this determinant, the delta of t, to be the van der Waals, and the van der Waals, they come outside. The first few derivatives are 0, just like what Loebner showed. And beyond n choose 2, here is the coefficient for every single power. And yeah, this again, this calculation by Loebner and these the Schur polynomial identities really lead to connecting between positivity preservers, majorization, and now the symmetric function identities from sort of which have been studied for quite a long time. One final remark with Siddharth Sahi in the preprint this year. This is when the variables UIs commute among themselves and the V's commute among themselves. These are what are called bosonic variables. And there are also fermionic variables where you have UIs anti-commuting. U1, U2 equals minus U2, U1. And G1, V2 equals minus V2, U1. And for that, we have some extensions. And not just for determinants, but also for permanents and for other sort of characters of the symmetric group. That's a technical remark for the end. So I guess that's it for now. Let me just end with some references. So these are the references for positivity preservers from Schur in 1911 to Schoenberg and Rudin with the converse theorem that no other functions work than the power series. And then there are some, these are some results. One thing I should point out is a bunch of these statements, most of these statements of these guys and a bunch of the proofs actually turn out to be present in this book, which also appeared this year, which is due to me. It appeared in Cambridge Press, but it will also come out in Trim series this year. But the point is, the book is sort of accessible to even sort of starting out grad students. So it's sort of a very introductory level book in the lecture note series. Here are some references to majorization from 1700s to 1800s to 1900s to 2000s. As I mentioned, there are more references in this by Cutler, Green, and Skandeva. And finally, here are references to symmetric function identities from Cauchy and Frobenius all the way to Rosengren and Schlosser and so on. Okay, thank you very much.
Other questions?